Continents are secretly connected by rivers of fire deep underground. Beneath the familiar map of our world lies a vast, hidden network of magma highways. This discovery completely rewrites the story of our planet, linking volcanic eruptions and the slow drift of continents to a single, subterranean system. By the end of this journey, you will see Earth not as a collection of separate lands, but as a single, dynamically connected planet. What force could possibly rip a continent in two? And why do chains of volcanoes appear in the middle of an ocean? What hidden geography lies beneath the ground you stand on? Alfred Wegener looked at a map of the world and saw a puzzle everyone else had missed. The coastlines of continents like South America and Africa seemed to fit together like pieces of a giant, fractured shell. He proposed a radical idea, continental drift, suggesting that the continents were not fixed in place but had slowly moved over vast stretches of time. His colleagues met this idea with deep skepticism. Without a clear mechanism to explain how entire continents could plow through the solid ocean floor, his beautiful theory was dismissed for decades. The missing piece of the puzzle lay hidden deep below. We now know the Earth's outer shell is not a single, unbroken layer, but is cracked into enormous pieces called tectonic plates. These plates, which carry both continents and ocean floors, are constantly in motion, floating on a hotter, softer layer of rock known as the asthenosphere. Think of them as colossal rafts of solid rock, slowly drifting on a sea of semi-fluid mantle. Their interactions are the engine of our planet's geology. Where plates pull apart, new land is born from rising magma. Where they collide, mountains are thrust towards the sky or one plate is forced beneath another. And where they grind past one another, they build up immense pressure that is released in violent earthquakes. This is the powerful framework of plate tectonics, the visible drama on the surface. But this understanding immediately raises a deeper, more compelling question. If these massive plates are moving, what immense, hidden force is actually pushing them apart and pulling them together? The answer lies in discovering the secret currents flowing beneath the plates themselves. Beneath the rigid plates of the lithosphere lies a world of profound change. This is the asthenosphere, a layer of the upper mantle where the rules of solid rock no longer fully apply. It is not a liquid, but under immense heat and pressure, the rock here becomes ductile, capable of flowing over geologic time like warm, thick asphalt. This vast zone acts as a planetary superhighway, a conduit for heat and material that stretches across the globe. Geophysicists peer into this hidden realm using a technique called seismic tomography. By analyzing how the energy from earthquakes travels through the Earth, they can map variations in temperature and density, much like a medical CT scan reveals the structures inside a human body. These maps reveal a dynamic landscape within the asthenosphere, with rivers of hotter, less viscous material flowing slowly between areas of cooler, more resistant rock. It is within this flowing layer that a critical transformation occurs. In regions where temperature and pressure are just right, a small percentage of the rock begins to melt in a process known as partial melting. This is not the creation of a vast underground ocean of lava, but the generation of individual droplets of magma that coalesce and begin to move. This newly formed magma is less dense than the surrounding solid rock, giving it buoyancy. It begins to rise, seeking a path upward, joining a massive, slow-motion circulation that drives the entire system. The asthenosphere is the grand central station of our planet's interior, the primary source and distributor for this fiery material. But a grand station needs tracks to guide its travelers. The journey of this magma is not a random, chaotic ascent. It is directed, focused, and channeled through specific, narrow pathways that reach from the flowing asthenosphere all the way up to the surface we walk on. These hidden pathways find their most dramatic expression along the longest mountain chain on Earth, a structure completely hidden beneath the ocean waves. Stretching for over 65,000 kilometers around the globe, the mid-ocean ridge system is a continuous, underwater mountain range where the planet's crust is literally tearing itself apart. Here, two tectonic plates are slowly pulling away from each other, creating a deep, gaping rift in the seafloor. This divergence acts like a release valve for the immense pressure building below. The separation of the plates reduces the weight on the underlying asthenosphere, allowing the hot, ductile rock there to decompress and rise. It is not a violent explosion, but a steady, persistent welling up of material from the planet's interior. This ascending mantle rock undergoes partial melting as it rises, generating vast quantities of magma that fill the void, cooling and solidifying to become brand new oceanic crust. The entire process functions like a colossal, slow-motion conveyor belt, constantly manufacturing new seafloor and pushing the older crust outward, away from the ridge. This is how oceans are born and how they grow wider over millions of years. To see this process in action, we can travel to Iceland, the one place on Earth where the mid-Atlantic ridge rises spectacularly above the surface. The entire island is a testament to this continuous construction. You can literally stand between two tectonic plates, with North America on one side and Eurasia on the other, and watch the ground between them slowly widen over a human lifetime. The landscape is dominated by volcanic activity, with geothermal vents and frequent eruptions that add fresh layers of rock, building the land higher and wider. This constant renewal leaves behind a permanent record of the planet's dynamic history. As the new volcanic rock cools, magnetic minerals within it align with the Earth's magnetic field, freezing that orientation in stone. Scientists studying the seafloor have discovered that this magnetic alignment is not constant. It forms a series of symmetrical stripes on either side of the ridge, recording the repeated reversals of Earth's magnetic poles throughout geologic time. This striped pattern is the ultimate proof of the seafloor spreading process, a barcode of planetary history written in stone. The mid-ocean ridges show us one half of the planet's great circulatory system, the place where new crust is forged and begins its journey. But if new crust is constantly being created, a fundamental question arises. Where does all that old crust go? If new crust is constantly being forged at the mid-ocean ridges, then our planet must possess an equally powerful recycling system to maintain its balance. This return journey occurs along the second great pathway, the subduction zones. Here, the story of the oceanic plate reaches its dramatic conclusion. Instead of pulling apart, two tectonic plates collide, and the denser, older oceanic plate is forced to bend and plunge deep beneath the other, which may be a lighter continental plate or a younger oceanic plate. This is a descent into an environment of almost unimaginable pressure and scorching heat. As the slab of rock sinks dozens and eventually hundreds of kilometers into the mantle, it is subjected to incredible forces that fundamentally change it. The intense friction and increasing temperature cause the subducting plate itself to release its hidden cargo, water. This is not free-flowing water, but molecules of H2O locked within the minerals of the oceanic crust, remnants of its long interaction with the sea. And this water is the key that unlocks the next stage of the magma's journey. When these water-rich minerals are carried down into the hotter mantle, they undergo a chemical breakdown, releasing their water into the overlying mantle rock. This release acts like a powerful flux. Water dramatically lowers the melting point of the surrounding mantle rock, a process you might compare to sprinkling salt on ice to make it melt at a colder temperature. This triggered melting generates new magma, which, being buoyant and less dense than the solid rock around it, begins its inevitable ascent. It forces its way upward through cracks and weaknesses in the overlying plate, creating vast magma chambers that fuel some of Earth's most iconic and powerful volcanoes. This entire process forms a majestic and often dangerous arc of volcanoes on the surface, parallel to the deep oceanic trench that marks the subduction zone. The most spectacular example of this is the Ring of Fire, a horseshoe-shaped belt that encircles the Pacific Ocean. From the Cascades in North America to the volcanoes of Japan and the Andes in South America, this ring is a direct and visible testament to the power of subduction. Mount St. Helens, for instance, is a product of the Juan de Fuca plate sliding beneath the North American continent. The famous, devastating eruption in 1980 was a violent release of the magma that had been building deep below, a stark reminder of the dynamic and living planet we inhabit. Subduction zones are the planet's ultimate recycling lanes, completing a grand, global cycle. The same crust that was born from magma at a mid-ocean ridge millions of years earlier is eventually consumed, melted, and returned to the mantle, only to potentially rise again someday as part of a new volcanic island or mountain. This intimate link means a volcano in the Pacific Northwest is geologically connected to a hidden trench off the coast, and both are part of the same hidden highway that started with a flow of material in the asthenosphere. But not all volcanic activity fits neatly into the story of colliding or separating plates. Far from the edges of any tectonic boundary, in the middle of the vast Pacific Ocean, a chain of islands rises from the deep, telling a completely different story. These are the Hawaiian Islands, and their existence points to a second, independent network of fiery highways rising from the very depths of our planet. These are mantle plumes, narrow, intensely hot columns of rock that originate unbelievably deep within the mantle, perhaps even at the boundary with Earth's superheated core. Think of them not as part of the broad, slow currents of the asthenosphere, but as isolated, powerful blowtorches fixed in place, aiming their heat directly at the underside of the Earth's crust. The Hawaiian island chain is the spectacular surface expression of this process. The Pacific Plate, a massive slab of the lithosphere, is slowly drifting northwestward. As it moves, it passes directly over a stationary mantle plume. The plume continuously melts the plate above it, punching through to create a volcano. Once that volcano is carried away by the plate's motion, the plume simply melts a new hole in its new location, creating the next island in the sequence. This is why the Hawaiian Islands are arranged in a long, graceful chain, with the big island of Hawaii currently sitting over the hotspot and actively erupting, while the older islands to the northwest are extinct and slowly eroding back into the sea. This provides a stunningly clear record of the plate's direction and speed over millions of years. These deep-seated hotspots offer more than just a beautiful geological clock. They provide a rare window into the composition of Earth's deep interior. The magma that erupts from hotspot volcanoes like Kilauea has a chemical signature distinct from the magma generated at mid-ocean ridges or subduction zones. This tells scientists that its source is different, coming from a reservoir of ancient rock that has been isolated from the shallow, well-mixed mantle for billions of years. The existence of mantle plumes reveals a far more complex and layered system of magma transport than the simple conveyor belts of plate tectonics alone can explain. It suggests that our planet's internal heat engine operates on multiple levels simultaneously, with broad asthenosphere currents moving the plates and deep, focused plumes independently piercing through them. This hidden network is not one single system, but a web of interconnected and independent pathways, all working together to shape the ever-changing face of our world. Mapping these hidden highways required a technological breakthrough, a way to see through thousands of kilometers of solid rock. The key was not to dig, but to listen. Seismologists discovered they could use the planet's own rumblings, the powerful energy released by earthquakes, to create a three-dimensional portrait of Earth's deep interior. This technique is known as seismic tomography. It works on a principle similar to a medical CT scan, where numerous X-ray measurements are combined to reveal the structures inside a human body. In this case, the X-rays are replaced by seismic waves. When a major earthquake occurs, it sends shock waves racing through the entire planet. By deploying networks of sensitive instruments called seismometers across the globe, scientists can precisely record the arrival times and behavior of these waves. The journey of a seismic wave is not uniform. It speeds up when passing through cold, dense rock and slows down significantly when moving through hotter, softer material. These subtle differences in travel time are the data points. By analyzing millions of these readings from earthquakes around the world, powerful computers can invert the data to build a detailed map of the Earth's interior, highlighting regions of varying temperature and density. One prominent seismologist described the challenge as trying to piece together the shape of a distant mountain using only the echoes that return from it. The initial data was often messy and open to interpretation, but over decades, a clear and stunning picture began to emerge. These tomographic images revealed the colossal, sinking slabs of oceanic plates in subduction zones, descending like stone waterfalls into the mantle. They illuminated the vast, warm rivers of the asthenosphere, flowing slowly between the continents, and they confirmed the existence of mantle plumes, those narrow, intensely hot columns rising from the deep, which create volcanic hotspots like the one under Hawaii. This non-invasive imaging was nothing short of revolutionary. It provided the first concrete, visual evidence that the planet's interior is not a static, layered sphere, but a dynamic and intricately connected system. The scale of these networks is almost beyond comprehension, with flows of material that stretch for thousands of kilometers, linking the fate of a volcano in one hemisphere to the slow drift of a continent in another. These geochemical fingerprints provide a second, more intimate layer of evidence, a forensic toolkit for the planet's interior. While seismic tomography reveals the physical structures, geochemistry tells us the life story of the magma itself. Every volcanic rock carries within it a hidden chemical code, a record of where it came from and the long journey it took to reach the surface. The key to deciphering this code lies in isotopes and trace elements. Isotopes are different versions of the same chemical element, atoms that have the same number of protons but a different number of neutrons. Some of these isotopes are stable and remain unchanged over billions of years, while others are radioactive and decay at a steady, predictable rate. The precise ratios of these isotopes in a volcanic rock are like a unique signature, inherited from its source deep within the Earth. Trace elements, present in only minute amounts, add another layer of detail, acting as clues about the specific conditions of melting and travel. A geologist in a laboratory can take a sample of basalt, the most common volcanic rock, and by analyzing these chemical fingerprints, determine its origin with remarkable precision. For example, the basalt that erupts at a mid-ocean ridge has a specific isotopic signature. It points to a source in the upper mantle that has been largely stripped of certain volatile elements, a reservoir scientists call depleted. This makes sense, as this part of the mantle has been repeatedly melted over Earth's long history to form the oceanic crust. In stark contrast, the basalt from a hotspot volcano like Hawaii tells a completely different story. Its unique isotopic ratios suggest it came from a far deeper and more primitive source, a reservoir of rock that has been isolated from the well-mixed upper mantle for billions of years. This is the geochemical evidence for a deep mantle plume. The most complex chemical narrative comes from the volcanoes of subduction zones. Here, the magma's signature is a messy, blended story. It carries the distinct imprint of the ancient, recycled oceanic crust and its overlying sediments, which were dragged down into the mantle and then melted, mixing their chemical identity into the new magma. You can literally detect the geochemical ghost of an ancient seafloor within the lava erupting from a volcano in the Andes. This forensic geochemistry reveals a crucial truth about the hidden magma highways. They are not simple, isolated pipes. They are complex, blending networks where different streams of material from various depths and origins meet, mix, and create entirely new compositions. A single volcanic eruption can therefore be the product of multiple sources, a cocktail of melted plate, mantle rock, and ancient seabed. This chemical evidence paints a picture of a dynamic and interconnected interior, a planet constantly stirring its own deep ingredients. It confirms that the slow currents of the asthenosphere and the fiery plumes from the deep are not just moving rock, they are transporting distinct chemical reservoirs across the globe, linking the surface to the most profound depths. So if these chemical trails can map the magma's past, could they also help us predict its future and the powerful geological events that shape our world? This grand planetary dance of magma and rock operates on a timescale almost impossible to grasp. It orchestrates the most epic performance in Earth's history, the Supercontinent Cycle. For billions of years, our planet's landmasses have rhythmically assembled into a single, colossal supercontinent, only to be torn asunder once more. And the hidden magma highways are both the stagehands and the directors of this entire production. When continents collide and merge into a supercontinent, they do more than just create a vast new landscape. They act like a massive, insulating blanket, trapping the Earth's internal heat beneath them. The mantle under this supercontinent begins to overheat, its temperature steadily rising over millions of years. This buildup of thermal energy cannot be contained forever. Eventually, it triggers the formation of a superplume, a monstrous upwelling of hot rock that ascends from the deep mantle and presses forcefully against the underside of the supercontinent. The landmass, weakened from below by this immense thermal pressure, begins to dome upward and crack, rifts form, and the supercontinent starts to break apart. The breakup of the ancient supercontinent Pangaea provides the clearest example of this cycle in action. As the superplume swelled beneath it, Pangaea was stretched and fractured. A long, linear rift opened, splitting the single landmass into separate continents. Into this growing wound surged the hot material from the asthenosphere, rising to fill the gap and solidifying as new oceanic crust. This was the birth of the Mid-Atlantic Ridge, a volcanic highway that continues to push the Americas away from Europe and Africa to this day. The Atlantic Ocean is not a static body of water. It is an ever-widening scar from Pangaea's dissolution, a direct result of the magma flowing from that ancient superplume. This perspective completely transforms our understanding of the planet. The hidden magma highways are not passive features. They are dynamic, responsive systems that actively drive the long-term evolution of Earth's geography. The assembly and dispersal of continents is a slow, majestic dance, and the heat and flow from the deep mantle provide the music and the choreography. Far beneath the plains of Africa, a planetary giant is stirring. Known as the African Superplume, this colossal upwelling of hot rock originates near the Earth's core and rises through the mantle like a slow-motion pillar of fire. It is not a narrow blowtorch like the Hawaiian hotspot, but a vast continent-scale anomaly that sprawls beneath most of Africa and reaches far out under the southern Atlantic and Indian Oceans. Its influence is written across the entire landscape, lifting the continent to an average elevation far higher than any other, a feature geologists call the African superswell. This is not a coincidence of random uplift. The superplume's immense heat makes the rock beneath the continent buoyant and less dense, causing the entire lithosphere to dome upward, much like a piece of wood held over a flame will warp and rise. You can see the direct consequences of this uplift in the dramatic geology of East Africa. Here, the continent is not just high, it is actively cracking apart. The East African Rift Valley is a massive, Y-shaped scar on the Earth's surface, a place where the crust is stretching and thinning. As the superplume swells beneath it, the African plate is being pulled and torn, creating a network of deep valleys, steep escarpments, and numerous volcanoes like Mount Kilimanjaro. This rift is a living laboratory, a snapshot of a continent in the very process of breaking in two. The ongoing research here is focused on a pivotal question. Is the African superplume the primary engine driving this continental rupture? Scientists are meticulously measuring the slow, incremental widening of the rift, monitoring the paths of magma as it rises to feed the volcanoes, and modeling the immense forces at play. The evidence increasingly suggests that we are witnessing the very early stages of a new ocean being born. Over millions of years, the rift could widen further, allowing the sea to flood in and eventually separate the Horn of Africa from the main continental mass, just as the Atlantic Ocean formed from the breakup of Pangaea. This single, deep-seated feature connects the deepest parts of our planet to the most profound surface transformations. The African superplume demonstrates that the hidden highways of magma are not just passive pathways, but active, powerful forces that can lift entire continents and tear them asunder, reshaping the world map over geologic time. Deep beneath the Pacific Ocean, a geological mystery of staggering proportions lies anchored at the very floor of the mantle. Here, seismic waves slow down dramatically as they pass through a region so vast it dwarfs every continent on the surface. This is the Pacific Large Low-Shear-Velocity Province, one of two continent-sized blobs of material sitting just above the Earth's core. These are not simple piles of hot rock. They are thought to be denser and chemically distinct, composed of material that may have been isolated from the rest of the mantle for billions of years. Imagine them not as part of the churning circulation, but as ancient, stable mountains rooted to the core-mantle boundary, immense and seemingly permanent. Their existence solves a major puzzle in the story of mantle plumes. If these hot, rising columns originate from random patches of the lower mantle, their distribution would be scattered. But the map tells a different story. Many of the world's most famous volcanic hotspots, including Hawaii and the volcanoes of Samoa, are geographically clustered above the edges of these deep, dense provinces. This has led scientists to a compelling hypothesis. The LLSVP may act as colossal thermal anchors. Their dense material efficiently traps heat from the planet's core, creating vast, stable hotspots at their boundaries. This intense, focused heat then powers the formation of the mantle plumes that rise toward the surface, feeding the volcanic island chains we see. This means the Hawaiian hotspot and the entire chain of islands it has built could be directly tethered to this primordial structure deep below. The material erupting from Kilauea volcano might carry within it a chemical signature inherited not just from the deep mantle, but from a specific, ancient reservoir that has survived since the Earth's violent infancy. This introduces a profound new layer to our understanding. The hidden highways of magma are not just temporary features. They are fed by deep, stable sources that connect the geology of today to the very formation of the planet. The existence of these primordial blobs suggests that our planet's interior is not a perfectly blended cocktail, but a layered and complex history book with chapters from its earliest days still preserved and actively shaping the world above. The same fiery processes that build continents also forge the very foundations of our modern world. These hidden magma highways are not just abstract forces, they are the planet's primary foundries, creating immense concentrations of valuable metals. One of the most prolific metal factories lies deep under the ocean, along the same mid-ocean ridges where new crust is born. As seawater percolates down through the fractured, hot rock, it gets superheated by the underlying magma chambers. This fluid becomes a powerful, acidic solvent, leaching metals like copper, zinc, and even gold from the surrounding volcanic rock. This mineral-rich, superheated water then surges back up through the crust, and when it hits the cold ocean water, it precipitates out its dissolved metals, building towering, black smoker chimneys. These hydrothermal vents are more than just bizarre ecosystems. They are actively forming massive sulfide deposits on the seafloor, vast undersea ore bodies that hold tremendous economic potential. On land, a different magmatic process creates another class of treasure. In subduction zones, as water-rich magma rises through the continental crust, it can stall in vast underground chambers. Here, the magma cools slowly, and the metals it carries, such as copper, molybdenum, and gold, become concentrated in the remaining fluid. This super-enriched fluid then forces its way into cracks in the surrounding rock, where it cools and solidifies into what geologists call a porphyry deposit. These are the giants of the metal world, the source of over half the world's copper and a significant portion of its gold and molybdenum. The Andes mountain range, a product of subduction, is studded with these incredibly rich porphyry copper mines. So when you hold a coin or look at the wiring in your home, you are holding a product of these deep earth processes. The copper was likely born from the slow cooling of a magmatic chamber that itself was fueled by a sinking tectonic plate and the water it carried into the mantle. This tangible link reveals a profound truth, that the planet's deepest inner workings are directly responsible for concentrating the mineral wealth that our technological society depends on. These deep earth processes do more than build mountains and concentrate metals. They hold the thermostat for our entire planet. The same hidden highways that transport magma also act as a planetary ventilation system, releasing gases that have, at times, dramatically reshaped the global climate. The most profound examples are the flood basalt events, colossal volcanic outpourings that dwarf anything in recorded history. These are not eruptions from a single mountain, but the fracturing of the Earth's crust on a continental scale, where lava floods across the landscape for hundreds of thousands of years. The geological formations they leave behind, known as large igneous provinces like the Deccan Traps in India or the Siberian Traps in Russia, are the scorched evidence of these cataclysms. They are now widely linked to the surfacing of massive mantle plumes, those deep-seated blowtorches punching through the lithosphere. The lava itself was destructive, but the true global impact came from the gases. These eruptions released staggering volumes of carbon dioxide and sulfur dioxide directly into the atmosphere. The result was a runaway greenhouse effect, a period of intense global warming that radically altered weather patterns and acidified the oceans. The timing of these events is chillingly coincident with some of the most severe mass extinctions in Earth's history. The end Permian extinction, often called the Great Dying, aligns with the Siberian Traps and saw the loss of most life on the planet. The end Cretaceous extinction, which claimed the dinosaurs, coincides with the Deccan traps in India. In these moments, the planet's internal heat engine, channeled through its magma highways, became an agent of profound planetary change. Yet this same system also possesses a built-in cooling mechanism. The very rock created by volcanic activity plays a crucial role in regulating atmospheric carbon over millions of years. When fresh volcanic rock, particularly basalt, is exposed to air and rainwater, it undergoes a chemical breakdown known as weathering. This process slowly draws carbon dioxide out of the atmosphere, locking it away in carbonate minerals that eventually wash into the ocean and form limestone on the seafloor. It is a slow, steady drawdown that counteracts the sudden, violent releases. This creates a long-term feedback loop between the solid Earth and its gaseous envelope. The magma highways bring heat and gases to the surface, which can warm the planet, while the resulting new rock slowly scrubs the atmosphere, contributing to cooling. This dynamic interplay, operating over millions of years, has been a fundamental architect of Earth's habitability, alternately challenging life and then restoring a balance. It is a humbling reminder that the ground beneath our feet and the air we breathe are part of a single, deeply interconnected planetary system. Yet for all we have mapped, a fundamental engine remains shrouded in mystery. What is the primary force that drives this entire system, that pushes and pulls the colossal plates and churns the mantle? Geologists are still debating the planet's deepest motive, and the answer is not as simple as it seems. One compelling theory points to the cold, heavy slabs of oceanic lithosphere sinking into the mantle at subduction zones. In this model, the dominant force is the pull of gravity on these dense, descending plates. Imagine it as a massive, slow-motion tablecloth trick, where the weight of the sinking edge drags the entire sheet of the plate along behind it. The rest of the plate is essentially being pulled from its leading edge, with the upwelling of hot material at mid-ocean ridges seen as a passive response, simply filling the gap left behind. This view of plate tectonics is driven from the top down by the cooling and sinking of old, dense rock, but another school of thought argues the real power comes from below. This model emphasizes the buoyancy of hot mantle plumes and the broad, rising currents within the asthenosphere. Here, the primary drivers are these massive upwellings, which press against the underside of the plates, pushing them apart and setting the entire system in motion from the bottom up. In this scenario, the sinking slabs are still important, but they are more a consequence of the system than its main engine. The debate is far from settled, with sophisticated computer models supporting different aspects of each theory. Some geodynamicists propose a balanced system where both forces, the push from hot upwellings and the pull from cold downwellings, work in a delicate partnership. This ongoing scientific discussion reveals a profound truth. Our map of the planet's hidden highways is still incomplete, with the very nature of Earth's immense heat engine remaining one of its most compelling unsolved puzzles. The next great leap in understanding our planet's fiery heart will not come from looking down, but from drilling deeper than ever before. Ambitious international projects are now aiming to do what was once pure science fiction, to physically reach down and retrieve a sample from the Earth's upper mantle. The International Ocean Discovery Program represents one of these monumental efforts, a plan to drill through the thin oceanic crust at the bottom of the sea and into the mysterious rock layer beneath. Success would mean holding a piece of the mantle in our hands for the first time, a pristine sample uncontaminated by its journey through the crust, offering a definitive chemical portrait of the engine that drives our world. This is not a simple task. It requires drilling through kilometers of hard rock under immense pressure and extreme temperatures at the bottom of a deep ocean, a staggering engineering challenge that pushes the limits of our technology. Alongside these physical probes, a silent revolution in sensing is unfolding on the seafloor. New arrays of advanced seismometers and other sensors are being deployed across the oceanic plates, creating a vast, permanent network to listen to the Earth's subtle whispers. These instruments act like a planetary stethoscope, detecting the faintest tremors and magma movements with a clarity we have never before possessed. They will trace the precise pathways of individual magma bodies as they rise from the asthenosphere, mapping the hidden capillaries of the Earth in real time. Back in the lab, our ability to comprehend this flood of new data is being supercharged by next-generation supercomputers. These machines are building virtual Earths inside their processors, simulating the incredibly complex dynamics of the entire mantle system over billions of years. Researchers can now run experiments that would be impossible in the real world, testing different theories of what drives plate tectonics, or watching how a superplume develops from the core-mantle boundary all the way to the surface. One of the most tantalizing goals of this digital and physical exploration is to solve the mystery of the Large Low-Shear-Velocity Provinces, those continent-sized blobs at the base of the mantle. Are they purely thermal anomalies, or are they also chemically distinct, representing the primordial building blocks of our planet that have survived for 4.5 billion years? A sample from the mantle, combined with data from new seafloor sensors and refined supercomputer models, could provide the definitive evidence we need. We may finally witness in high resolution how a droplet of magma forms deep in the asthenosphere, navigates the complex filter of the lithosphere, and ultimately erupts at a volcano. The discoveries of the next decade will not just add footnotes to our geological textbooks, they promise to rewrite entire chapters, bringing the hidden highways of magma into a focus we can scarcely imagine today. Long before we ever mapped the asthenosphere, humanity was telling stories about the world below. Ancient cultures across the globe described the underworld not as a cold, dark place, but often as a realm of fire and molten rock. In Greek mythology, the god Hades ruled a subterranean kingdom bordered by fiery rivers. Norse legends spoke of Muspelheim, a world of flame whose heat was said to predate the sun itself. These were not just random inventions. They were powerful, intuitive interpretations of the very real geological forces that people witnessed shaking the ground and lighting up the mountains. A volcanic eruption was the breath of an angry god, an earthquake the stirring of a chained giant deep within the earth. These myths gave a name and a face to the terrifying, unseen power that rumbled underfoot. They represent our earliest attempts to explain the unexplainable, to find meaning in the chaos of our dynamic planet. This deep-seated cultural fascination connects us directly to our ancestors. They looked at a volcano and saw a divine forge, while we look at the same mountain and see a vent for a mantle plume. The object of wonder is the same, only our framework for understanding it has evolved. Their poetic metaphors have given way to our seismic tomography and geochemical analysis, but the core human impulse to comprehend the hidden world remains unchanged. Our modern scientific narrative, with its hidden highways of magma, is the latest chapter in a story humanity has been telling for thousands of years. It is a story that satisfies that ancient curiosity with the profound power of evidence, revealing that the truth beneath our feet is more interconnected and more magnificent than any legend could have conceived. The same volcanic forces that forge metal and reshape continents also create sanctuaries for life in the most desolate places on Earth. Miles below the sunlit surface of the ocean, along the jagged slopes of mid-ocean ridges, scalding water rich with dissolved minerals and gases billows from cracks in the seafloor. These are hydrothermal vents, and they are oases of profound activity in the perpetual darkness. The energy that powers these entire communities does not come from the sun, but from the planet's own internal heat, channeled directly through the hidden magma highways. As seawater seeps down through fractured rock and gets superheated by the magma below, it undergoes a radical chemical transformation, becoming a toxic, mineral-laden fluid. When this fluid erupts back into the icy cold water, it creates towering chimneys of precipitated minerals, and it is in this turbulent, chemical-rich environment that life has found an astonishing way to thrive. The foundation of this entire ecosystem is a process called chemosynthesis. Here, specialized bacteria perform a miracle analogous to photosynthesis, but instead of using sunlight for energy, they use the chemical energy from hydrogen sulfide and other compounds pouring out of the vent. These bacteria are the primary producers, the grass of this sunless world, turning the Earth's own geochemistry into biological fuel. This discovery completely rewrote the rules of biology, proving that life could build a world entirely independent of solar energy. These bacterial colonies support a menagerie of creatures found nowhere else on the planet. Dense clusters of pale tube worms, some over 2 meters long, stand like a forest of swaying stalks, their red plumes absorbing chemicals from the water which they then provide to the bacteria living symbiotically inside their bodies. Giant white clams with blood that uses hemoglobin to transport sulfide instead of oxygen bury themselves in the mineral-rich sediment. Blind, ghostly white crabs scuttle across the rock, grazing on the thick mats of bacteria. This is a food web built not on light but on fire, a direct biological consequence of the planet's internal heat engine. The realization that such complex ecosystems could flourish powered solely by planetary chemistry sent shockwaves through the scientific community. It fundamentally expanded our understanding of where life can exist, both on our world and beyond. If a hidden magma highway can fuel a lush community in the crushing pressure and eternal night of the deep ocean, then similar energy sources could very well exist on other icy, dark worlds. The subsurface oceans of moons like Europa and Enceladus are now prime targets in the search for extraterrestrial life, as they may harbor their own hydrothermal systems, heated not by the sun but by the gravitational tug of their parent planets. The discovery of these deep sea vents revealed a universe of possibility hidden within our own, proving that the energy flowing through the Earth's interior does far more than move continents. It breathes life into the deepest, darkest corners of our world. Our planet's churning interior is not the cosmic norm, but a spectacular exception. To truly appreciate the dynamism of Earth's hidden magma highways, we need to leave our world behind and view it from a broader perspective. Mars presents a stark and silent contrast. The red planet is a world of stalled geology, dominated by a single, staggering feature, Olympus Mons. This is not merely a large volcano, it is a behemoth, so vast it would cover the entire state of Arizona. On Earth, our tectonic plates are constantly drifting. This movement prevents a single volcanic hotspot from building a mountain in one place for too long, creating instead chains of islands like Hawaii. But Mars lacks active plate tectonics. Its lithosphere forms a single, unbroken shell, a stagnant lid. With no plates shifting, a fixed mantle plume was able to pour lava out at the same location for billions of years, constructing Olympus Mons layer by layer into the tallest mountain in our solar system. This frozen landscape tells a story of a world whose internal engine has largely shut down, its magma highways fallen into disuse. Our own moon offers an even more extreme example of geological stillness. Its surface, scarred by ancient impacts, has remained almost unchanged for 3 billion years. The moon is a cold, solid body, its interior heat long since dissipated, with no active magma flows to reshape its face or erase the craters of its violent youth. Then there is Venus, a world shrouded in mystery and clouds. Radar maps reveal a surface covered in volcanoes, yet there is little evidence of current, Earth-like plate tectonics. Scientists debate whether Venus experiences a different style of resurfacing, perhaps in catastrophic episodes where the entire planet's crust is recycled in a massive, global volcanic outburst, followed by long periods of quiet. This comparative view of our celestial neighbors reveals a profound truth. Earth's constant, steady recycling, driven by its interconnected magma systems, is remarkably rare. This ongoing geological activity is far more than a spectacle. It appears to be a fundamental requirement for a world that remains alive and habitable over billions of years. The hidden highways of magma are not just a feature of our planet, they may well be the very pulse of a living world. The pace of this planetary system operates on two distinct clocks. On the one hand, the grand, sweeping currents of the mantle that move the tectonic plates are almost imperceptibly slow. The entire Atlantic Ocean is widening at roughly the same speed your fingernails grow, just a few centimeters each year. This is the timescale of continents, a stately dance measured in millions of years. Yet within this slow-motion framework, individual travelers move with surprising urgency. Once a blob of magma has formed and gained buoyancy, its final ascent through the last few dozen kilometers of brittle crust can be remarkably swift. It can force its way through fractures and pre-existing weaknesses in a matter of days, weeks, or months, pooling in chambers just beneath a volcano. This creates a fascinating paradox. A volcano like Mount St. Helens was built over hundreds of thousands of years by the slow, relentless motion of the Juan de Fuca plate sliding under North America. Yet the magma that ultimately caused its catastrophic eruption in 1980 may have raced upward from its deep storage zone in a geological instant. The final trigger for an eruption often involves a complex interplay of pressures, where the sudden arrival of new, hot magma from below can destabilize a chamber that has been simmering for centuries. This means the hidden highways have different speed limits. The broad, deep currents in the asthenosphere are a sluggish, continental drift, while the narrow, vertical conduits feeding individual volcanoes are the express lanes. This interplay between the incredibly slow and the surprisingly fast is what makes our dynamic planet both stable over eons and suddenly volatile within a human lifetime. Yet this entire system depends on a seemingly ordinary ingredient, one we interact with every day. Water is the silent partner in this subterranean drama, a catalyst that transforms solid rock into mobile magma with an efficiency that heat alone could never achieve. The journey begins not in the mantle's depths, but at the bottom of the ocean, where water saturates the volcanic rock of the seafloor. When an oceanic plate is pulled down into a subduction zone, it does not descend alone. It carries with it a colossal cargo of this bound water, locked within the crystal structures of minerals like serpentine. This is not free-flowing water, but water that has become a fundamental part of the rock's chemistry. As the plate sinks deeper, the increasing heat and pressure force these water-bearing minerals to break down in a process called dehydration. They release their water not as a liquid, but as a superheated fluid that infiltrates the overlying wedge of mantle rock. The rock of the upper mantle, known as peridotite, is incredibly resilient, with a melting point that is normally far too high to be breached by ambient temperatures alone. But when this subducted water is introduced, it acts as a powerful flux. You can think of it like salt scattered on an icy road. The salt does not add heat, but it disrupts the structure of the ice, causing it to melt at a much lower temperature. The water does the same thing to the atomic bonds within the peridotite, dramatically lowering its melting point by hundreds of degrees. This triggered melting creates a unique kind of magma, one that is hydrous or water-rich. And this water content changes everything about the magma's behavior. Hydrous magma is far less viscous than its dry counterparts. It is thinner, more fluid, and able to navigate the microscopic pores and tiny fractures within the solid mantle matrix. This reduced viscosity acts as a lubricant for the entire system, allowing the magma to coalesce into larger droplets and migrate upward with far greater ease. Without this watery assist, the mantle would remain largely solid, and the vibrant volcanic arcs that line our continents would never form. So the next time you see steam rising from a volcanic vent, remember you are witnessing the final release of a journey that began millions of years ago in an ancient ocean. This profound connection reveals that the water cycling on our surface is intimately linked to the fire churning below, completing a planetary cycle that truly makes Earth a world of interconnected spheres. As magma forces its way upward, it does not travel through an empty pipe. It intrudes into a complex landscape of pre-existing rock, known as the country rock. And this journey is not a passive one. The intensely hot magma acts like a geological solvent, partially melting and dissolving the walls of its own passageway. This transformative process is called crustal assimilation. Think of a clear mountain stream. As it flows downhill, it erodes its banks, picking up silt, minerals, and organic matter. By the time it reaches the valley, the water is no longer clear but carries the distinct character of every landscape it has touched. Magma behaves in a similar way. A mass of basaltic magma born from the mantle might have a specific dark chemical signature, but if it pauses in a large chamber within the continental crust, which is typically made of lighter, silica-rich rocks like granite, it begins to melt and absorb that material. The magma is literally changing its own recipe. It incorporates this new melted crust, which increases its silica content and alters its mineral makeup. Through this process, the original basalt can be transformed into andesite, a rock common in volcanoes like those in the Andes. With even more assimilation, it can become rhyolite, a light, high silica rock that fuels the planet's most explosive eruptions. This is a primary reason for the staggering diversity of volcanic rocks we find on Earth. The magma highways are not sterile, insulated tubes. They are dynamic, interactive pathways where the traveler is fundamentally altered by the very ground it moves through. A single volcanic eruption can therefore offer a blended sample of our planet, containing whispers of the deep mantle mingled with the ghosts of ancient continental rock. This intricate network of magma highways is not merely a subject of academic curiosity. It forms the very foundation of a life-saving science, the art and science of predicting volcanic eruptions. By understanding these hidden pathways, we learn to interpret the vital signs of a restless planet. The techniques used by volcanologists are, in essence, methods for detecting traffic jams and construction projects deep within the Earth. They listen for the subtle tremors that signal magma forcing its way through cracks, a phenomenon known as an earthquake swarm. These are not massive, single quakes, but thousands of tiny, sharp fractures as rock gives way to the ascending molten rock. It is the sound of the highway being actively excavated. Scientists also measure the ground itself as it subtly changes shape. As a magma chamber fills deep beneath a volcano, the entire landscape above it can begin to swell and uplift like a giant, slow-motion balloon. This ground deformation is tracked with incredible precision using networks of GPS stations and satellite-based radar, a technology called INSAR, which can detect bulges of just a few millimeters. This tells researchers that a reservoir is filling, that pressure is building. Perhaps the most telling clue comes from the gases the magma releases as it rises. Just like opening a warm bottle of soda, the reduction in pressure allows dissolved gases like carbon dioxide and sulfur dioxide to escape. A sudden increase in these emissions, especially the ratio between different gases, is a strong indicator that fresh, volatile, rich magma is moving into the shallow parts of the system. Each of these signals alone is a piece of the puzzle, but when seismic activity, ground swelling, and gas emissions all increase in concert, it paints a compelling picture of an imminent eruption. This integrated monitoring approach transforms our abstract geological map into a real-time early warning system. A detailed understanding of a volcano's specific plumbing, the exact routes and chambers that magma uses, allows for dramatically more accurate forecasts. Knowing that a volcano tends to store magma in a shallow chamber just 5 kilometers down, for instance, means that once movement is detected, the time to an eruption could be relatively short. Conversely, a volcano with a deeper primary reservoir might give scientists a much longer lead time. This knowledge directly translates to saved lives and protected property, allowing for timely evacuations and community preparedness. The hidden highways of magma, once a mystery, have become a roadmap for resilience, turning our deepest fear of the Earth's power into a tool for safeguarding our future upon it. Carbon, the fundamental element of life, is also a restless traveler on the planet's deepest highways. Its journey begins on the seafloor, where the skeletal remains of countless marine organisms made of calcium carbonate settle into the sediments. Over millions of years, this carbon-rich sediment and the altered volcanic rock of the ocean crust are carried down into the mantle at subduction zones, dragged to depths of immense pressure and heat. This is the start of an epic descent, a voyage into a realm where carbon can be transformed and transported in ways we are only beginning to grasp. Some of this subducted carbon does find a quick return ticket. As the sinking plate heats up and releases its water, it can flush carbon dioxide back toward the surface, where it fuels the explosive eruptions of arc volcanoes, returning the gas to the atmosphere. But a significant portion of this carbon seems to vanish, traveling much deeper into the Earth's interior. It may descend past the point of easy return, drawn down by the relentless pull of the cold, dense slab. Current research suggests that some carbon could be carried all the way to the core-mantle boundary, a journey of nearly 3,000 kilometers. Here, in the profound darkness and pressure, it might be stored in colossal reservoirs or incorporated into exotic minerals like diamonds, which form under these extreme conditions. This deep carbon cycle operates on a timescale of hundreds of millions of years, a slow, rhythmic exchange between the surface world and the planet's fiery heart. It represents a hidden climate regulator of staggering capacity. The carbon dioxide in our atmosphere is just a tiny fraction of the planet's total carbon budget, the vast majority of which is thought to be locked away in this deep reservoir. The occasional catastrophic release of this deep carbon, perhaps through a superplume event, is a leading suspect for triggering past episodes of intense global warming and mass extinctions. Conversely, the steady, long-term drawdown of carbon through subduction and its deep storage helps to cool the planet over geologic time. This reveals that the stability of our climate is not just a surface affair, but is intrinsically tied to the traffic flowing along these hidden magma highways, a slow-motion dance between the air we breathe and the deepest depths of our world. Beneath the familiar cacophony of our world, the planet itself generates a constant, low-frequency hum. It is a symphony of subtle vibrations, born from ocean waves crashing on distant shores and atmospheric winds brushing against the surface. For decades, this ambient seismic noise was considered mere static, an inconvenient background fuzz that geophysicists had to filter out to hear the clear signals of major earthquakes. But a revolution in listening has turned this noise into one of our most powerful tools for seeing into the Earth. Scientists discovered that by deploying vast arrays of sensitive seismometers and recording this endless hum, they could use it to illuminate the hidden world below. The technique relies on a principle called cross-correlation. Imagine two microphones placed on opposite sides of a noisy, crowded room. By mathematically comparing the recordings from both, you could tease out the specific sound path between them, effectively mapping the acoustic space. Researchers apply this same logic to the Earth's hum. They take the continuous, seemingly random vibrations recorded at two different seismic stations and cross-correlate the data. The result reveals the green's function, the fundamental impulse response of the ground between those 2 points. It is as if a virtual earthquake occurred at one station and was recorded at the other. By doing this for thousands of pairs of stations across a region, scientists can stitch together a detailed, three-dimensional image of subsurface structures, all without waiting for a single actual quake. This is like learning the shape of a hidden room by listening to the echo of the constant, gentle rain falling on its roof. For mapping magma highways, this is a game changer. Active volcanoes have notoriously complex and ever-changing plumbing systems. With ambient noise tomography, researchers can create frequent, high-resolution snapshots of these hidden pathways. They can watch as a magma body slowly inflates a chamber deep underground, trace the development of a new fracture network, or identify the precise conduit that fed a recent eruption. It provides a quieter, more continuous surveillance of the planet's fiery corridors, offering a real-time window into their dynamic nature. This method allows us to hear the Earth's inner workings not just during its violent shouts, but in its perpetual, whispering breath. This same underground fire has always sparked a different kind of creation in the human spirit. For centuries, the volcano has stood as more than a geological force. It has been a profound metaphor in art and story, a symbol of the raw, untamed power that simmers just beneath the surface of things. The Romantic painters of the 18th and 19th centuries were drawn to eruptions not as disasters, but as sublime spectacles. In the works of artists like J.M.W. Turner, volcanoes like Vesuvius are depicted as cathedrals of flame, their fiery plumes illuminating the night sky with a terrifying and beautiful light. These canvases are not just records of an event, they are meditations on the awe-inspiring power of nature, a force that dwarfs human concerns and speaks to something ancient and primal within us. The volcano represented the ultimate sublime, the thrilling point where beauty and terror become one. This artistic fascination reflects a deep, intuitive understanding of the hidden world we have been exploring. The solid ground of the landscape, like the calm facade of our daily lives, can be ruptured at any moment by a force from below, a surge of transformative energy that reshapes everything. The concept of magma highways, these channels of liquid rock flowing beneath a solid crust, finds a powerful echo in the way we think about human creativity itself. We often describe a burst of inspiration as something that erupts, that flows up from a hidden wellspring within the mind. We speak of ideas simmering below the surface until the pressure becomes too great and they break through into conscious thought. The artist's studio, the writer's desk, the composer's quiet room, these can be the subduction zones of the human psyche, where experiences and emotions are drawn down, compressed by time and pressure, and transformed into something entirely new. Just as water is the essential catalyst that allows mantle rock to melt and become mobile, so too is often a catalyst for our own creative breakthroughs, a substance that unlocks what is solid within us and allows it to flow. The hidden highways of magma remind us that stability is not the same as stillness. Our planet is alive because it moves and churns within, and in the same way, Our own richest expressions often come from acknowledging and tapping into the depths we cannot always see. To understand the Earth's interior is to receive a lesson about our own potential, a reminder that the most powerful transformations often begin far beneath the surface, in the hidden forges of the heart and mind. So we arrive at a unified vision of our planet, where these seemingly separate forces are revealed as threads in a single, magnificent tapestry. The mid-ocean ridge is not an isolated factory, but the beginning of a conveyor belt. The subduction zone is not merely a destructive sink, but a powerful recycling plant. The mantle plume is not a random anomaly, but a deep-seated blowtorch. And beneath it all, the vast provinces like the LLSVP act as the stable anchors and thermal engines for the entire system. This is the true nature of the hidden highways, a global network for the transfer of mass and heat that governs everything from the rumble of an earthquake to the very air we breathe. It is this interconnected flow that forges the copper in our technology and over billions of years has regulated the planet's climate, alternately warming it with volcanic gases and cooling it through the slow weathering of the rock it creates. The familiar map on our wall, with its fixed continents and blue oceans, is an illusion of the moment. The real map is three-dimensional, dynamic, and forged in fire. It is a map of currents and conduits, of rising heat and sinking rock, a system where an event at the core-mantle boundary can ultimately dictate the chemistry of a volcano on the other side of the world. This realization transforms Earth from a collection of separate lands into a single, breathing entity. We are not living on a finished sculpture, but on the ever-changing surface of a living, churning, and profoundly connected world. Our journey began with a single, fractured map and a radical idea. It has carried us through the discovery of tectonic plates, into the flowing rock of the asthenosphere, and down to the primordial blobs anchored at the Earth's core. We have traced the invisible pathways of magma that silently bridge continents, connecting a volcano's eruption to the slow descent of an ocean floor thousands of kilometers away. This exploration reveals a planet alive with constant movement and profound connection, where processes occurring in the deepest mantle directly sculpt the mountains, oceans, and air of the world we inhabit. The ground you stand on is not a final destination. It is a single, temporary point on a vast, dynamic circuit of heat and rock, a system that forges our resources and regulates our climate over immense spans of time. If this descent into the Earth's hidden corridors has sparked a new wonder for you, we would love to hear your reflections in the comments. Subscribe to continue exploring the world's greatest mysteries with us. The final chapter of our planet's story is far from complete, its next pages being written right now, deep in the fire below.